All right. So as we have discussed in the previous lecture is regarding the concept and the origin of the graph theory. That is the first topic as per our course. Let us define what is the definition of a graph. It's not like you drawing a graph as per your school, that is in a graph paper which you are doing as x axis and y. So this is a completely wrong things as I define a graph. But a graph is a consisting of, it's generally denoted by a G, and it's an order pair of two sets. I can say it is V of G and E of G, okay, or is just defined as V order pair V and E. So it's consisting of two finite sets, where V of G is known as a vertex set. Is a vertex set of the graph. And E of G, and which may or may not be, which is non-empty set. Okay, and E of G, or just E, it is called an edge set of the graph, which possibly empty set of element. So V is a non-empty set. Always the vertex set is non-empty, but E is may or may not be empty. Okay, so it may possible there will be a no edge in the graph. E is possibly empty set, possibly, but it's not always be non-empty. It may be possible that an edge set is an empty set. Every element of E assign an unordered pair of vertices in V, and it's called the AND vertices of the edge E, and that's composed with the definition of the graph. So what I am saying is every element E, so the element of this is a set, its element we generally denoted by a small letter. E of E is assigned as an order pair, as an unordered pair of vertices UV, and it's called an AND vertices of the edge. E. So this E, it's called the edge, and U and V are the AND vertices of that, and all this together is forms a graph. I am repeating again, what do you mean by a graph? A graph is an order pair consisting of two sets. One is a vertex set, Another one is the age set. V is a non-empty set and E is possibly empty set. Every element of E assign a 2 unordered pair. It's not necessary 2, it may be many also, but it is always assign an unordered pair of vertices, and that unordered pair, it's called the end vertices of the edge E. All this together is forms a graph. I will give you an example of a graph. For example, this is a vertex. So a graph consisting of only one vertex. So this is known as a vertex. So this is a graph, I can say. So this is a graph G1, I may write. If we can have 3 vertices and one edge, this is also a graph. So generally vertices are denoted as U, V, W, small letters. And this is the edge E1. So this is, I can say, a graph G2 altogether. So as per the definition, it has an order set. What is E is here? It is only consisting of one set, E1. And what is the vertex set in this case? It is U, V and W. So actually this graph G2 is a EV. It is an order pair, sorry, VE. As per the notation we have used VE. So it is order pair E, where first will denote vertex, which is U, V, W. Edge set is E1. And every element of this edge set, that is E1, assign as per this, assign an unordered pair of vertices U and V. So that is, this E1 is assigned edge vertices, that is V and W. So this all together forms a graph. Let me give you one more example. Let's say you have a graph like this with 5 vertices, and you may take this as a graph. My figure means this is not correct, but you may draw in this manner. So this is graph G3. So these are some examples of graph I have plotted in front of you. Now when you have a graph, there will be 2 things we should know: that order of the graph and the size of the graph. So the first one is order of a graph G. Order of a graph G. So order of the graph G is the nothing but the, what is this notation? The notation is the number of element in V. Number of elements in V is denoted by this. Okay, the number of elements in V. And if the number of elements in V is n, then the order of G is n. So how the order is defined? A number of vertices in graph G. For example, in this first graph G1, the number of vertices is 1. So that's why the order of this G1 is 1. Order of G2 will be 3 because there are 3 vertices. Order of G3 will be 1, 2, 3, 4, 5. Since this G3 has 5 vertices, so that's why order of this G3 is 5. The next definition is the size of graph G. A size of graph G is mod of E. This is number of vertices in E. That is the number of edges in the graph. If it is M, then the size of G is M. What is the size? Size is nothing but the number of edges in the graph G. For example, in this graph, there is 0 edges are there. So, in graph G1, the size is 0. In graph G2, the size will be 1 because it has only one vertex. And in graph G3, it is 1, 2, 3, 4, and 5. So there are 5 edges. So the size of this G3 is 5. A next definition is a self loop. And the word itself suggests its definition. Self loop. What does it mean? If you have any edge E in a graph G, which having identical end vertices. What is mean by end vertices on edge? I have already defined earlier. See, end vertices of then E is an edge, U and V, if they are the end point, then they are called the end vertices of any edge. If this U and V is same, then it is called a loop or a self loop. So, what is the definition? The edge having identical end vertices, it's called the self loop. For example, in this graph, if I have a graph with the 4 vertices, and if I draw like this, and if I draw this as a graph, or this as one edge, this is one edge. So there are V1, V2, V3, V4. There are 4 vertices, and E1, E2, E3, E4, E5, and E6. There are 6 edges. Here E6 is a self loop. That we can conclude from this. The next definition is the parallel edge. Here the word itself suggests what should be the definition of parallel edge. So can somebody give me a definition of parallel edge?
Sir, if two edges, दो endpoints अगर edges के same हो, then the edges are parallel.
So such edge having the same vertices as both its end vertices, it's called the self loop. Okay, that is the same. So a parallel edges is in one edge, or there are 2 vertices having end points of 2 edges. Okay, 2 different edges. It's like this situation. So what is the definition? Is more than one edges associated with the given pair of vertices. More than one edges associated with given pair of vertices. it is called an parallel edges. Okay, which refers, this edges refers to parallel edges. For example, if I draw a graph like this, this is one graph, and there are V1, V2, V3 and V4 are the vertices, and E1, E2, E3, E4 are the edges. Then here the more than one edges, that means E3 and E4 associated with the given pair of, I should write AND vertices. Okay, so the AND vertices are V4 and V3, and this pair of AND vertices associated with two edges, that is E3 and E4. So I can say that E3 and E4 are parallel edges. Okay, so they are the parallel edges. A next definition is a simple graph. So what is the definition of a simple graph? A graph which does not contain a parallel edges or a self loop, it is known as a simple graph. A graph that has neither self loop nor parallel edges, it's called simple graph. For example, this graph is not a simple graph. This graph is also not a simple graph, but I can say that this graph G1, G2 and G3, all these three graphs are a simple graph, or I can draw any other graph. Here they are the examples of a simple graph. So this is an example of a simple graph. Then the next definition is a multigraph. What is a multigraph? A multigraph is a graph of order pair G is equal to VE with V a set of vertices. This is also known as a nodes. There is another name of the vertices is also known as a node, and E is a multiset of unordered pair. Unordered pairs of vertices called edges. This is known as a multigraph. So what will be the example of a multigraph? I can say that the example of a multigraph is this, which contains a parallel edges, and this one, which contains a self loop. So I can draw an example of a multigraph is, so this is the graph. This is the example of a multigraph. Okay. Then the next definition is the finite or infinite graph. Means finite graph and infinite graph. So if you want, you can just give the two separate title for the finite graph and for the infinite graph. A finite graph in a graph in which a number of edges are finite. Okay. And the number of vertices also finite. Number of edges as well as number of vertices are finite. It's called the finite graph. So graph with a finite number of vertices as well as finite number of edges. It's called finite graph. And what is the infinite graph? Otherwise. Called infinite graph. In our course of a graph theory, we'll only talk about the finite graphs. We'll never talk about the infinite graphs. Okay. So the graph, so all the above graph which I have given a definition, all of them are finite graph, because in that the number of vertices and the number of edges are finite. But if I can define a graph like this, and this goes on and on, this grid is, if this edges are not there, this is also not there. And if I plot it in this manner, if this is a grid, like a grid, and this grid is infinite, let's spread it. Okay, so this is an example of infinite graph. Our discussion is only based on the finite graphs, never goes on the infinite graph. Now, the first question should come in our mind is why we have to study a graph theory. So for that, I need to talk some of the application of graph. Some of the applications of graph we should learn. The one of the application we have discussed in my previous lecture. In that we have discussed the Konigsberg bridge problem, or it's well known as a 7 bridge problem. Let us recall what is this 7 bridge problem again. So there is a Konigsberg is one of the city in Russia. Okay, and in that city there is a river. It's situated like this, and there will be Iceland. 2 islands are there. One is here, another one is here. So this city is actually divided into 4 parts. First part, second part, third part, and the fourth part. And on this river, there are 7 bridges. This is the first bridge. This one is a second bridge. Here is a third one, which connects C and D. And this is the fourth one, is also connecting B and C. There is one more bridge which connect both this Iceland, C and D. And there is one bridge which connects A and D, and one bridge which connects B and D. And the problem is to know, and the problem was actually Euler's has mentioned in its research paper in 1736, and it is a long-standing problem until it's solved by Euler's. Okay, and he wrote a paper, a research paper on a graph theory, and there is people are known, that is the result is known as the originated of the graph theory. And the problem is you have to travel every bridge of this river exactly once without repeating it, and you have to reach back to the same part. That means if you start with A, then you have to visit every bridge of this, every bridge. So there are 7 bridges, so you have to travel all the 7 bridges and come back at the same place. That was the problem, and the problem was solved by Euler in 1736 in his one of the research paper. And this problem can be expressed or can be visualized in a graph theory with the help of vertices and edges into the following manner. That means if I plot here, it is my A, that is this Iceland or this bank of river, I can denote it as vertices A. Then another is vertices C, which is this Iceland, and this bank of river that is on the side of B we have denoted as B, and on the other side there is a D. Now the A which connect with C, there are 2 edges, so I can say there are 2 parallel edges are there. One is this, another one is, let's say, this one. C and B is also connect with the 2 parallel edges. So how we are denoting this, means how we are drawing this edges, if there is a pull or there is a bridge between B and C. A D and C is also connected, and A and B is also connected via one bridge. So I can say this is the bridge between them, and B and D is also connected. So this is the graph, and this graph is actually an output or visualization of representation, graph representation of this Königsberg bridge problem. And in Euler, he stated that the solution of this problem, he says that a connected graph. What do you mean by connected graph? That means there will be a path between every pair of vertices. What is mean by path, we'll discuss, but you can connect, you can correlate with that. Euler says that a graph is Eulerian graph. Eulerian graph means what I'm talking is this graph. That means if you start with any pair of any vertices, means if you start with here, you visit every edge of this graph, every edge of this graph, and if you come back at the same vertex, you have to visit every edge exactly one, and if you come back at the same vertex, then that graph is known as Euler graph. And it says that if graph is Euler, if and only if every pair or every vertices, all vertices of G is even. Now, what do you mean by even degree? Even degree means number of vertices are number of edges are connect to this vertices A. The degree of this A is 1, 2 and 3. The degree of this vertex is 1, 2, 3, 4, 5. Likewise, the degree of this one is 1, 2, 3 and degree of B is 1, 2, 3. This statement says that a graph is Eulerian. That means such path is possible if all the vertices are of even degree. Here in this graph, you can just note that this graph is not Eulerian due to this result. So thus this type of walk is not possible. The 7 bridge, you have to walk over all the 7 bridges exactly one and return back to the starting point. Now it is interesting. This is out of the subject. It is well known to know that out of the 7 bridges, still there are 5 bridges are still there on this city. The 5 bridges are there. 2 bridges which is destroyed in World War II. In World War II, the 2 bridge, which are the one of this bridge and one of this 2 bridge, will be destroyed in the World War II, and all other 5 bridges are already there. And in the history, it says that this problem is originated of the graph theory. Sorry. The next problem is to find the shortest path. Problems of finding the shortest path problem. And this problem is very much useful in internet surfing also, to delivering a goods to its warehouses or delivering goods to a shops from the warehouses, or delivering a goods to a company, or the company want to deliver goods through flight to the different cities. So how a flight management is also a finding, it's having the base in the finding the shortest path between 2 cities. If suppose I want to travel from London or from here Ahmedabad to London, then and you are searching on the internet that my journey starts from the Ahmedabad and ends at the London, then how the search engine will work so that it will give you a shortest path. That means maybe a flight reach to first Dubai and then it will reach to London and so on. So there are different type of options will give, but what is the mechanism behind it? It's actually finding the shortest path between these 2 vertices, because if you can draw all the flights on the world, and then you can see that suppose there are different cities These are the different cities, and there is a connection of this city to this city, and it may happen that it will not connection from this city to this city directly. So what will be the shortest path to joining this two city? So such problem is finding a shortest. Such problem is known as a shortest path problem, and there are different algorithms will be studying in this. It is some of the name I can give you: Disaster's algorithm, then Flure's algorithm, and Warsaw algorithm. There are many algorithms are there. So these are the few applications of this graph theory is we can give, and there are various other applications you can find in the engineering, physics, biosciences, neural networks, and number of areas which you cannot count. The graph theory is that much useful nowadays. So now let us go into the detail of the graph theory and some of the very elementary concepts to develop the graph theory. It's the first concept is the incidence and the degree. A degree, almost I have told you what do you mean by degree, and what is the incidence, it's correlated with that. So when the vertex Vi is an AND vertex of some age Vj, Vi and Ej are said to be incident with each other. Okay, so for example, if I have a draw this graph, I can draw this as a graph, and there are V1, V2, V3, V4 and V5 vertices, E1, E2, E3, E4, E5, E6 and E7. There are 7 edges. So I can say that this E2 and E1 is incident with V1. What I'm saying? E1 and E2 are incident with E1. That is easily seen because this is there and this is one is joining with E1. So that's why it is incident. The next definition is the adjacent. Adjacent two non-parallel edges. Two non-parallel edges are said to be adjacent edges if they are incident on a common vertex. For example, in this graph, E1 and E2, so as per this, the two non-parallel edges are said to be adjacent if they are incident on the common vertex. So I can say that E1 and E2, they are adjacent edges. E4 and E6 are the adjacent edges, but E2 and E6 is not an adjacent edges. Okay, so this is the definition of, sorry, it is adjacent vertices is there. Yeah, incident common vertex. So I can say that this is about the edges, incident edges. So for example, we may write that E1 and E2 are the adjacent edges. In graph G, what is the graph G is this, if I can call? Now the same way, this is the definition of adjacent edges. In the same way, we have definition of adjacent vertices. Two vertices are said to be adjacent if they are n vertices of same age. For example, here I can say that V2 and V3 are the adjacent because they are end of E4. But I cannot say that V2 and V4 are adjacent. Okay, so that we can write as an example that V2 and V3 are adjacent vertices, but V2 and V4 are not adjacent vertices. Now the next definition is the degree. Now using this adjacent and incident, we can able to define a degree. Let V be a vertex of graph G. The degree is denoted as VD of V. Of V is the number of edges of G incident with E. Sorry, with V, counting. So you have to count the self loop twice. Okay. For example, in the above graph, so this V2 is, I can say it is incident with 3 edges, E2, E3 and E4. So therefore the degree of V2 is 3 because there are 3 vertices, this one and this one is incidental. So the degree of V2 is 3. A degree of V3 is 1, 2, 3. It is also 3. Degree of V4 is also 1, 2, 3, 4 because this is the self loop, and the self loop we have to count twice. Okay, so it is 1, 2, 3, 4. The degree of V4 is 4. In the same manner, you can able to write down is I want this table that you can calculate the degree of each vertex, and I want this number from you guys. I'm giving you few minutes time to calculate this. I'm back to the figure. Calculate this. Calculate the degree of each vertex. Done? So what is the degree of V1? 3. Degree of V2? Degree of V3? 4? 4. What is degree of V5? 1.
1.
What will be the sum of all this degree? That means summation I running from 1 to 5, D of Vi is 14. Is this 14 is related with number of edges? Can you see that? This relation, how many edges are there?
7.
7. So is this related with, so I can say it is a 2 times 7. Will it be true for in general any graph? That means if I have a sum of all the degree, then that will be sum 2 times the number of edges, and it is always there. Why? Because you are counting. See, when you have counted for E1, how many times this E2 will be counted? 2 times. One for this when you calculate the degree of V1, and another time when you calculate the degree of V2. So the contribution of this E2 edge is 2 times. Okay, and so on. For every edge you have counted twice. So contribution in the degree of any edge will be 2 times. If it is a parallel, sorry, if it is a self loop, then it is also twice we are counting. So that's why what we can write as one of the theorem which is true for any graph, the statement of the theorem we can write in this manner is for any graph G, with E is the edge set, edge with E edges and N vertices. Let's say the vertices are V1, V2 up to Vn. Then what we can say is summation of I running from 1 to N, P of Vi is 2 into E, 2 times E. E is the number of edges, and this is true for any graph G. What you have to write down in the proof, as I have explained you, that each edge, since it has a two end vertices, contributes precisely 2 to the sum of the degree of the all the vertices in G. When the degree of the vertices are summed, each edge is counted twice. That is the just 2-line proof you can give for this argument or proof of this theorem. Let me write, so you can have your notes here. Each edge since it has 2 vertices contributes precisely 2 to the sum of the degree of all vertices in G. When the degree of the vertices are sum of each edge is counted twice. This is the proof. A next definition is the odd vertices and even vertices. What does it mean of odd vertices and even vertices? A degree of any vertices is odd. It is known as odd vertices. And the degree of the any vertices is even. It's called the even vertices. So that is the definition of even vertices, odd vertices. Okay, a graph or vertex of graph it's called odd if degree of vertex is odd. Now I hope that you can write down the definition of even yourself. That means if it is even here, then the degree will be even. So for example, in the above graph, so there are 1, 2, 3, 4 are odd number of vertices and 1 is an even number of vertices. Okay. So what you can say from this? How many? Let me give you one more example. Okay, here in this graph, what we have observed is there are 1, 2, 3, 4. There are odd number of vertices are 4. Okay. Let me give you one more example of a graph. So the objective is to calculate, you can plot any graph, whatever you wish. Let me plot in this manner. So I want that everyone in this group They can plot their own graph. They can plot their own graph and try to find out number of degree of each of the vertex and try to see what is happening there. So the degree of V1 is 1, 2, 3, 4. Degree of V2 is 1, 2, 3 here. Degree of V3 is 1, 2, 3, 4. 4 here. Degree of V4 is 1, 2, 3. V5 is 2. So here there are odd number of vertices are 2. And I hope that everyone having the odd number of vertices in their respective graph will be even.
Yes,
So
sir.
Yes, sir.
yeah. So what is the conclusion we can make out of this? Is in any graph there are even number of odd vertices. There are even number of odd vertices, and that is known as a handshaking lemma. So I'm just writing in the one line. In any graph G, there are even number of odd vertices. Okay, this is known as a theorem, and the theorem is a handshaking lemma. And why it is known as handshaking lemma? You can correlate with the statement. The statement is this: any graph G, there are even number of odd vertices. So you should write the same thing here. Why it is known as handshaking lemma? Can somebody explain this? The handshaking lemma. So try to correlate by yourself. Why it is known as even number of odd vertices. Okay. So you can start with some group of people. You can start with some group of people and see what is happening in the group of people. How many number of odds handshake will be there. So we can correlate with that. So that's why it is known as handshaking lemma. How to prove this statement? It means any graph G, there are even number of odd vertices. How to prove this? So we have already discussed that earlier. That means this theorem, in that we have seen that a sum of all degree will be 2 times a number of edges. Okay. So let G is a graph. E1, E2 up to En are the vertices, and E is the number of edges in the graph. So as per the above discussion, we can say that summation I running from 1 to n d of Vi is equal to 2 times E. Now in this d of Vi, there are a number of odd vertices and there are number of even vertices. So this summation I can split into 2 parts. Those vertices which having even degree and those vertices which having odd degree. So this summation I can split into 2 parts. The first one is even, d of V I may write, and plus summation odd. So what we are doing is we are separating this summation into two summations. In the first one, we will put all those vertices which having the even degree. And in the second summation, we are writing all those vertices which having the odd degree. Now, what is the sum of even numbers? So this each of d of vi is a even number now. What you can say about a sum of even number is always even. A sum of even number, any two even number you add, that will gives me a even number. So we can note that, the sum of even number is always even. Okay, so that means this is a even number, this number is even. If I subtract that number from this 2 times e is also an even number. So that means what we can say here is all the odd vertices, sum of all vertices is 2 times e minus summation even is there. This quantity is an even number and it is subtracting from the even number. So what I can say, even number is subtracted from the even number is again even. So what is the statement we have is proved by this argument that the sum of odd vertices is even number. Okay, so I can say this is even minus even is even. Just write, if you want, you just write down the reason that difference of two even number is even, if you want, for your convenience. So ultimately what we have proved is there are even number of odd vertices, because this is the even number and this there are number of odd vertices are there. The next definition is isolated vertex. So what do you mean by isolated vertex? A vertex which having no incident edges is known as isolated vertex. A vertex having no incident edges, it's called isolated vertex. Okay, for example, if I have this is the graph, this is the graph where v1, v2, v3, v4 and v5 are the edges, then v3 is isolated vertex. So it's not adjacent to any of the graph, any of the edges. The next definition is a pendant vertex. Pendant is like pendulum. So the word itself suggests that what should be the definition of pendant vertex. A vertex of degree 1, it's called the pendant vertex. Vertex of degree 1, it's called pendant vertex. For example, in the graph, if I plot this as a graph, okay, this is the vertex, and this is V, I can say 5, V5 is a pendant vertex. The next definition is the null graph. A null graph in which the edge set is empty. A graph in which the edge set is empty, it's called the null graph. I will not write this, you can write in your words if you want. A null graph is a graph in which edge set is empty. That means there is no edges. So if I can consider, this is the graph, is graph G is a null graph. The example of a null graph is no edges will be there. And next is very important concept called isomorphic graph or isomorphism. Iso means one. So the concept is the same. Suppose I have this graph G1 and I plotted this graph G in this manner. And the same graph G I may draw in another manner. This is G2. So what is the difference between G and G2? Is nothing, just I have plotted this edge and I am giving you different notation also here. Let's say this is V1, this is V2, V3, and this is, I may plot this is as E1, E2 and E3. Here may we vary with W1, W2, W3, and the edges we denoted as, let's say, F1, F2, F3. So here these two graphs actually looking at the same, because what we have did is just this edge E3, in this it is plotted in this form F2. So whenever such type of two graphs are there, they are look equal, they are same, but I cannot say geometrically or in the way it is look like it is not same. So G1 and G2 are not same graph, but they are isomorphic graph. Okay, so there is isomorphism between these two. So now I hope that you will understand what you mean by isomorphic graph. The graph is graph which are different graph, but there is a one-one correspondence between these two graphs. Okay, so such graphs are known as isomorphic graphs. So let me give you a definition, proper definition of this isomorphic graph. If I have a graph G1, a graph G1 which consisting of two sets E1 and V1 and E1 is said to be isomorphic to graph G2 which also consists two sets order pair V2 and E2 if there is a 1-1 correspondent between the vertex set V1 and V2 and 1-1 correspondence between the age set E1 and E2 in such a way that E1 is an age with and vertices U1 and V1 in G1, then the correspondence age E2 in G2 has its and vertices U2 and V2 in G2, which corresponds to U1 and V1 respectively. And in such pair of correspondence are called isomorphism. Such pair of correspondence it's called graph isomorphism. So in other words, I can say a two graph G1 and G2 dash are said to be isomorphic if there is a Verman correspondence between their vertices and between their edges such that incidence relation is preserved. For example, in the graph which I have talked, here I have just defined a label in different manner, but the graphs are isomorphic graphs. So in that way, the one-one correspondence is there. That means if V2 is joined with two incident vertices, then corresponding to that V3, sorry W3 here, which for example I can say there is a one-one correspondence between V2 and W3. One-one correspondence between V3 and W2. There is a one-one correspondence between V1 and W1. And similarly, there is a one-one correspondence between E1 and F3. One-one correspondence between E2 and F1. And one-one correspondence between E3 and F2. So this is the unknown, I mean this what I am explaining here regarding the one-one correspondence between two pair of sets, which is a vertex set and the edge sets. Let us give you one more example here regarding the isomorphism. So let's plot in this manner. So there are 6 vertices U1, U2, U3, U4, U5 and U6. I can plot this in this manner. So this is the graph G1, I can say. Graph G2 is I'm plotting as V1, V2, V3, V4, V5 and V6, and which can be plotted in this manner. The lines are not taking straight, but you can understand. So this is the graph. Okay, and this is graph G2. This G1 and G2, they are actually isomorphic graph. So I am writing a question here. Example. So that G1 and G2 plotted here are isomorphic. They are an isomorphic graph. First of all, if I can say that there is a 1-1 correspondence, that means there is a number of vertices and number of edges should be same in both the graph. Then only then there is a 1-1 correspondence we can establish. Otherwise, we cannot establish the 1-1 correspondence between them. And we can see that there are number of edges and number of vertices are the same in both the graph. There are number of vertices are 6. How many number of edges? 9. So there are 9 edges in this G1 graph and also in G2 graph. So first we should note that a number of edges and number of vertices are the same. They are same. And there is a 1-1 correspondence between every pair of vertices here. For example, U1 is, if I fix with V1, then U1 is connect with V4, V5, V6. Here, V1 is connect with V6, V2 and V4. Okay. So out of this V4, V5, V6, any one of them, V2, either V2, V4, V6, will be correspondence between this U4, V5, V6. So now what are the left? Two things are left. V3 left and V5 left. So this U2 and V3 has correspondence with V3 and V5. So let's say U2 is corresponds with V3. Now what will happen? Now what is left is U3. So obviously the U3 will correspond with V5. And in similar manner, if V5 is covered, now V4, V2 and V6, these 3 vertices are left. And if you consider V6, V6 is connect with U1 is over here, U2 is covered and V3. Okay. So what you have is U6 is corresponds with V6 and U5 left, or you can also having the correspondence instead of this. If you want, you can just write down U5 is correspond with V6. any one of the pair you can put it here. U1, U2, U3, U4. U4 is left, which you can corresponds with V2, and U5 we can current with V4. You can also put that V5 is connect with U6, and also there is another pair is possible. U6 is connect with V4. Since there is this type of relation is there, we can say that these two graphs are isomorphic graph. But the next question that I am writing, that is for this graph, and this is the graph. The question is check whether this two graph or following two graphs are isomorphic. So what is your answer? See, first of all, number of vertices are same. 1, 2, 3, 4, 5, 6. Here also 1, 2, 3, 4, 5, 6. The 6 number of vertices are same. Number of edges are the same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The number of edges are the same. The vertices and the number of edges are the same. But what will happen? Suppose they are isomorphic, okay, then there will be a 1-1 correspondence between them two. But what is happening? Let's say, what is the difference I can found here? There are one edge, this X, which connect with two pendant vertices here. Is there any edge is there which connect with the two pendant vertices here?
No.
No. So that is, let's say here, this is my Y and this is W. And if I can say this is U and V, then this X must correspond to Y because the degree of X and degree of Y is the same. All other have the degree 1 or 2. Because this has degree 1, this has degree 2, this has degree 2. This X has a degree 3. And here the Y has a degree 3. No other vertex has degree 3. So that means this X must, if these two graphs are, so this is the graph G1 and this is the graph G2. And if you want that this G1 and G2 are isomorphic, this X must isomorphic to or 1-1 correspondence with Y. Because they have the same degree. So I can write X must corresponds to Y because they are no other vertices. There are no other vertices with a degree 3. But in the graph G1, there is a 2 pendant vertices, and in graph G2, there is only 1 pendant vertices. Okay. And this is the reason why these two graphs G1 and G2 are not isomorphic graphs. So therefore I can say there is only one pendant vertex adjacent to y. In G1, there are two pendant vertex U and V adjacent to X. So this leads that these two graphs are not isomorphic graphs. And there are various other examples you can do for your conveniency to check whether the given graphs are isomorphic or not. Ultimately, our objective is to know what is the isomorphic graph. It is the same graph but plotted in the different manner, so that they are known as in rough language I can say it is isomorphic graph. The next definition is a complete graph. See, we are just developing a terminologies of graph theory, and later on we'll use this all the terminology when we'll discuss some of the application. So, what is a complete graph? A complete graph is actually a simple graph. What do you mean by simple graph? There will be no edges, no parallel edges, and no loop. That is called simple graph. So complete graph is, first of all, it is a simple graph in which every pair of distinct vertices is joined by an edge. Every pair of distinct vertices are joined by a edge. It's called the complete graph. So a complete graph is a simple graph in which every pair of distinct vertices is joined by edge. So it is actually denoted by Kn. So if the n is the number of vertices. A complete graph is denoted by Kn. So what is K1? It only has one vertex. What is K2? Two vertex with one edge. As per the definition, every pair of vertices should be connected. Simple graph. K3. So there are three edges. This edge will connect with this one, this vertices which connect with this one, this has to be there. That's it. This is K3. What is K4? So there are four vertices. Every pair of vertices has to be joined. So this is K4. Try to draw K5, K6 and K7 yourself. Try to draw this, all this figure of K5, K6 and K7. And then count the number of vertices, if I denote the number of vertices as some notation here, so I may make table number of vertices. How many number of vertices are in K1?
0.
1. Sorry, not number of vertices, but I'm counting number of edges. I want to count number of edges. So there are 0 edges. Here there is number of edges is 1. Here 3. Here 6. Here 20. Here this is represent the number of edges. If you have plotted your graph, you can plot the graph first and then count. It has to be, and if you can have the correction, you can tell me this is 10, not 20.
Yeah,
How many?
yes.
How many are here? 21. Check. This is 28. You can check, find out. There are 21 number of edges are there, here 28. And you can observe something, that how I am writing this number. And you can have the answer to that, you can give me. The definition is in front of you, and definition itself gives you how many number of edges should be there. The definition is told you that every pair of vertices will be connected. Every pair of vertices. So suppose I'm trying to plot the K5. Then this vertices should connect all this. And if you use the probability here, then what is the probability that it will join all these edges? The counting principle is used here. So this is joined, this one is also joined, this one is also joined, this one is also joined. So how many times this will be there? This vertex is joined with how many number of edges? In particular, in this it is 4, but if there are n number of vertices, then n minus 1,
n minus 1.
N minus 1.
n minus 1 number of edges should be there with joined with this. Same for this one. Okay, same for this one. So this n minus 1, same for this one. And same for this one. Each and every vertex, we have the same concept. So how many times this n minus 1 comes? How many vertices are there? N vertices.
N.
So it is n into n minus 1. And when you join, it is count 2 times. Every time it will count, because one time you join this to this, and then again you join this to there. So that's why every time you have counted the number of edges twice. So that's why divided by 2. So in Kn, a number of edges are always n into n minus 1 by 2. That is a conclusion we can made out of this. And that's why I have written the 6 into 5 by 2. So this is wrong. It is 15.
Yes, sir, it is 15.
This is also wrong then. It is 7 into 6 by 2. 21. So this figure I have written here, 21. So in general, there are in Kn graph, there are n into n minus 1 by 2 number of edges. Okay, so let me write as a result this thing. So I can say it is a corollary that the maximum number of edges in a simple graph with n vertices is n into n minus 1 by 2. In other way, we can say that a complete graph has n into n minus 1 by 2 number of edges. Next definition is bipartite graph. Bipartition, partite means it is a partition. So a graph which partite, that means it is partitioned into two graphs. But it is not a partition of a graph, but it is a partition of the vertex set. Okay. So if you have a graph G and if it is a graph which consisting of two order pair V and E, if V is a graph which can partition into two non-empty, that means it can be partitioned into two non-empty whose intersection is phi and X is non-empty and Y is also non-empty, in such a way that each edge of X has, each edge of G has one end in X and another one in Y. So one end point it is in X, another end point it is in Y, and it has to be true for every edge in that. Then G it's called bipartite graph. For example, I can say that this graph is an example of a bipartite graph. So if I can say this is X, so I am dividing this graph into two portions. The first set in this vertices are this two. Another set, the vertices are this two. This is my set Y. So what is the definition says? A vertex set is divided into two parts, X and Y. So the union will be X. So in this there are two graphs, this vertex is divided into two portions, X and Y. Every pair, every edge, as per this, every edge has one end. So if you can consider any edge in this graph, so let's say this edge has one end in X, another one is in Y. So it has to be true for every pair of edges. So it is known as bipartite graphs. Okay, so this is an example of bipartite graph. This is also an example of a bipartite graph. this cycle is also an example of a bipartite graph. Why? You can see this. So if I call this as V1, V2, V3, V2, V3, V4, V5 and V6. Now V1 is connect with V2 and V6. So I am writing V1 here and V2 here and V6 here. Now V2 is connect with V3. So V2 is here. That is connect with V3. And V3 is connect with V4. So that should be here, V4. So the two vertices or two edges of V3 is over, V2 is over, V6 is connect with V1 and V5. So V5 is, you may plot here and you join them. V6 is over V4. V4 is connect with V3 and V5. So if I can divide the vertex set into two parts, that is V1, V3, V5, and another side is, this is my X set, this is my Y set. So this graph is actually isomorphic to this graph. This graph G1 is isomorphic to G2, and this G2 graph is a bipartite, so G1 is also bipartite graph. So this is an example. This also can be drawn in this manner. You can see this graph and this graph is same, because if you pick this two and you can open it like it is a fold, you will lead to this figure. So this is an example of a bipartite. This is also an example of a bipartite graph. In this case, the X is this portion. And this is X contains only one vertex, and all other will contain in Y. So it has to be partitioned into two parts. So vertices has been partitioned into two parts. It is called bipartite graph in such a way that every edge has one end in X, another one is in Y. Next definition is a complete bipartite graph. So what is a complete bipartite graph? It is a simple graph. First of all, it is a complete simple graph. It has to be bipartite. Okay. So a complete bipartite graph is a simple bipartite graph. First of all, what do you mean by bipartite? I have already explained you. Bipartite graph, and it is a simple, that means there is no loop, no parallel edges. With partition, that is V is X union V, Y. In bipartite, that it is not necessary that every pair of X will connect with every pair of Y. But here in the complete bipartite graph, every vertex in X is adjacent to every vertex of Y. So every vertex in X is adjacent to every vertex in Y. And if number of vertices in X is M and number of vertices in Y is n, then the complete bipartite graph is denoted by mn. So what will be the example of K22? That means the X set contains, this is my X and Y. It has to be bipartite graph. So every pair, every vertex has one hand in X, another one is in Y. And as per this, it says that every vertex in X is adjacent to every vertex in Y. So that means this edge, so this vertex is adjacent to this and this. This and this. There is no relation between in between. Okay, please keep in mind. So this is K22. Can you plot K33? Plot K34 also. So K33 is, there are 3 vertex here and 3 vertex on this side, and this 3 are joined. Same way this is also joined. Same way this also. So this is K3. K34, on this side there are 3 and on this side there are 4. You join them. This is K34 and so on. In this manner you can have any graph of such type. The question can be asked, or I can say, how many number of edges in KMN? How many number of edges should be there in KMN? So as per the
M into N.
M into N. Okay, that is easily seen from the definition. Fine. Now next definition is a regular graph, or I can say K regular graph. There are a couple of few definitions are left. We'll finish with this. K regular, a K regular graph in which every degree of the vertex will be fixed, K. Such graph is known as a K regular graph. Okay, this is true for every vertex V in G. For example, in this K22 is a K regular graph. Every vertex has degree 2. So it is a K regular graph. K33 is a K regular graph. Every vertex has degree 3. You can see that. In general, can I ask you that what is Kn? Is a K regular graph? How much degree in each vertex in Kn? What is Knn? Complete bipartite graph. Is a K regular graph? What is Kn? How many? You can see what is Kn. We have plotted here. Kn is this graph, complete graph. How many number of degree for this vertex? It is 4, and it is true for everyone. So in general, Kn is the n minus 1 regular. What is Knn? Kn is an n regular. For example, here K22, it is a 2 regular. K33 is a 3 regular. So in general, it is a n regular graph. Next definition is a directed graph. A directed graph in which the direction is important. Okay, so the directed graph is consisting of the order pair EG and VG and EG, where VG is the vertex set, maybe it is not, see, it is never empty, so it is a non-empty set, and it's called, the member of it is called the vertices or node. Another one is the edge set. This is the edge set. And edge set is possibility empty. Possible it is empty. But the definition of the graph and the directed graph is the difference is here. That means it is a directed edges here. Now in the definition of graph, we have used the word of on-order pair. Here it is the order pair. That means the direction is important. So it is whose element are called directed edges. Okay, and it's assigned an order pair. E of G is subset of this. It is assigned an order pair. For example, this is a graph. This is a directed graph. Example of a directed graph. So the direction is important. From here to there you can go, but you cannot go back. Like a flight. It may happen that there is a flight from Ahmedabad to London, but it may possible that from the London to Ahmedabad direct flight may or may not be there. So in that situation, this directed graph is important. So these are the examples of a directed graph. And when is a directed graph, that then there is a degree also you can define. It's called in degree and out degree. Okay. So in degree, the definition of in degree is a degree which are going into the vertex, and out degree, that means number of vertices which are going out from that. It is called out degree. Okay, so this is the things that I want to told you regarding the very basic concept of the graphs. We'll learn some more concept of a graph in the next lecture. So if you have any doubt, you can ask me.